So, uh, that specific frustration where you ask an AI a question, something maybe a little complex or multi-layered, and it comes back at you with this absolute unwavering confidence.
Oh, yeah, and yet if you actually take the time to check the facts, it's just completely embarrassingly wrong.
It's the worst, right? Because it's wrong, but it outputs the text with such conviction that you almost gaslight yourself for a second. You think, wait, maybe I'm the one who remembers that historical event incorrectly? But no, it's the hallucination problem. We've all been there where you ask for a specific connection between two things and the AI it just makes it up.
It's a classic failure mode for large language models. And honestly, it happens because traditionally, these models are simply generating the most probable next word based on statistical patterns they've seen in their training data. They aren't actually doing the rigorous work to verify the truth against external sources in real time.
All right, they're just pattern matching text. But today for you listening, we are doing a deep dive into a research paper that is trying to fundamentally rewire that behavior. We're looking at a paper titled CoRAG. That stands for Chain-of-Retrieval-Augmented Generation. And this comes out of a collaboration between researchers at Microsoft Research and Renmin University of China.
This is a really fascinating piece of work because it tackles that exact frustration you mentioned. It's attempting to move AI away from just guessing an answer based on a single initial search and moving it toward a framework where the system iteratively queries information, processes it, and refines its searches.
Yeah, instead of just blurting out a response, it actually breaks the problem down.
Exactly.
Yeah.
The framework they've built, CoRAG, is entirely about teaching these models to retrieve information, analyze what they found, realize if they are missing a crucial piece of information, generate a new search query, and basically reason in a continuous loop. It's a step-by-step problem-solving approach.
So our mission for this deep dive is to really focus entirely on the methodology behind this. We aren't just going to look at the final scores and say, well, it works better. We want to understand the mechanics. How do you actually build a system that learns to evaluate what it needs to look up? How do you teach it to admit a search failed and then try again?
Precisely. We need to examine how the authors generated the data to train the system because that data generation is a massive technical hurdle in itself. Then we need to look at the unified training process, and finally, how they implement this during the actual usage phase, which we call test time computation.
Right, letting the model run longer to get more accurate results.
Right.
But before we get to the author's solution, we have to really clearly define the problem they're trying to solve. Because I think a lot of people might assume that if we just make the AI models larger with more parameters, this hallucination issue just naturally goes away. Why is the standard way we do things right now failing us on these complex questions?
Well, let's establish the status quo first. Standard ARG, which stands for retrieval-augmented generation, is the setup used by most enterprise systems right now. In standard ARG, a user asks a question, the system takes that exact question, sends it to a search database, grabs the top few document results, feeds those documents to the AI, and prompts the AI to answer the user's question using only that provided text.
Which sounds totally logical. That's essentially how I use a search engine myself. I type a query, I click the top link, and I read the text.
And it works perfectly for simple, direct questions. If you ask, what is the capital of France, the system searches that exact phrase, it retrieves a document stating the capital is Paris, and the AI outputs Paris. It's done. But the authors highlight a specific category of questions where this single-step process completely breaks down. They refer to these as multi-hop questions.
Multi-hop meaning you have to logically connect one piece of information to another separate piece of information to fully resolve the original query.
Yes, exactly. You need intermediate facts. The paper uses a very specific example to illustrate this problem. It's a question about a movie called Dark Hazard.
Yeah, I have that example right here. The exact question from the paper is, where did the star of Dark Hazard study?
Now consider how a standard RGA system handles that prompt. It takes the entire sentence, where did the star of Dark Hazard study, and it uses that complete string of text to search the database. It is looking for a single document that contains references to the movie Dark Hazard, the concept of a star or lead actor, and an educational institution, all within the same block of text.
And practically speaking, that specific document probably doesn't exist anywhere in the database. A Wikipedia page about a 1934 movie isn't going to list the entire cast and their respective college backgrounds in the plot summary.
Right, so the search retrieval returns nothing highly relevant. Maybe it returns a short production summary of the movie Dark Hazard. The AI processes that summary, finds no mention of a college, and then it either outputs an apology saying it doesn't know the answer, or worse, it hallucinates. It might see the term movie star and just generate the name of a prominent acting school because statistically that word often follows actors in its training data.
It just fills in the blank with a highly probable but factually incorrect token.
Exactly. The fundamental problem here is an information gap. To correctly answer the question, you first need to identify who the star of the movie actually is. You literally cannot perform a successful search for the educational background until you have extracted that actor's name. Standard R attempts to execute the entire process simultaneously in one single retrieval step.
The paper also discusses a technical issue they call the by-encoder bottleneck, which plays a major role in why that initial search fails. Can we break that down purely in terms of the methodology?
Definitely. This relates to how modern text retrieval databases actually function. They don't just look for exact keyword matches. Instead, they use mathematical representations called vectors. The system converts the user's entire question into a continuous string of numbers, a single fixed-size mathematical array that represents the overall semantic meaning of the sentence. It also converts all the documents in the database into similar vector arrays.
Okay, so it's matching the numerical representation of the question to the numerical representation of the documents.
Correct. It measures the mathematical distance between those arrays. But the by-encoder bottleneck occurs because the model is forced to compress a highly complex multi-part question like, where did the star of Dark Hazard study, into one single fixed-size array? It has to merge the semantics of a specific 1930s movie with the semantics of higher education.
And when you compress multiple distinct concepts into one format, you lose the precise relationships between those concepts.
You lose the structural sequence entirely. The resulting array is a convoluted mixture of movie concepts and education concepts. When the system checks the database, that mixed array doesn't closely match the specific document about the movie, and it doesn't closely match the specific document about the actor's life. It lands in an empty mathematical space between the two topics.
So it returns irrelevant data. And there's another methodological issue the authors point out, right? The when problem.
Yes, the when problem refers to the rigid sequence of standard RAG. The system always retrieves external data first and then generates text second. But for complex reasoning tasks, you often do not know what specific information you need to retrieve until you have already begun processing the initial problem.
Because you might need to establish one basic fact before you even know what the second query should be.
Exactly. You have to establish the intermediate state. And that iterative loop is precisely what the CoRAG methodology is designed to replicate. The framework relies on chaining sequential retrieval steps together dynamically.
So let's trace how the CoRAG methodology actually processes that exact same Dark Hazard question. We established that standard ARG fails because it searches the whole sentence at once. How does CoRAG operate differently?
CoRAG begins by analyzing the original prompt. But instead of executing an immediate database search, the model is designed to evaluate its current state of knowledge. It processes the text and identifies that it is missing a prerequisite variable. It knows it needs to find an educational institution for an actor, but it does not have the actor's identity.
So it pauses the final generation and outputs an intermediate text string.
Right. It generates what the authors call a subquery. It formulates a new specific question based purely on what it needs to know first. It generates the text, what was the name of the star of Dark Hazard, and it sends only that specific subquery to the retrieval system.
Which is a much more direct prompt for the database.
Extremely direct. The retrieval system easily finds a document stating the star is Edward G. Robinson.
Okay, so now the system has retrieved that specific string, Edward G. Robinson, but it still hasn't answered the user's initial prompt.
And this is where the iterative methodology is crucial. The model takes that retrieved text, the subanswer, and updates its internal context. It now registers that the subject is Edward G. Robinson. Based on that updated state, it generates a second entirely new subquery. It outputs the text, where did Edward G. Robinson study?
And again, that creates a very clean, precise vector for the database to match.
Yes. The database processes that second subquery and retrieves a document containing the text City College of New York. Now, the model evaluates its context, confirms it has satisfied all the variables of the original prompt, and generates the final output, City College of New York.
When you break it down verbally like that, it seems like a very straightforward sequence of logic. But training a language model to actually execute that sequence, to output a subquery, wait for a response, evaluate the response, and then decide whether to query again or generate a final answer. That requires a very specific methodology. You can't just instruct a base model to do that without specialized training data.
That is the most significant methodological challenge addressed in the paper, because standard training data sets do not contain that sequential data.
This is what the authors refer to as the chicken and egg problem for training data. If you look at standard data sets designed for complex questions, they typically only provide the initial question and the final verified answer. They will list the question, where did the star of Dark Hazard study? And the answer, City College of New York.
Right. They provide the start state and the end state, but they completely omit the intermediate text. They do not record the separate subqueries or the subanswers required to bridge that gap. So the researchers face a major problem. How do you train a model to generate intermediate queries if you have 0 examples of intermediate queries in your data set?
You would theoretically have to manually write out the exact required subqueries for millions of training examples, which is obviously impossible.
It's completely unscalable. So to solve this, the authors detail a methodology called rejection sampling to autonomously generate their own intermediate training data. This is a critical component of their approach.
I really want to focus on rejection sampling because it sounds like a highly technical statistical process. How do they actually use this to create a data set from scratch?
They start with a standard capable language model that has not yet been specially trained for this task. They input a complex multi-hop question from an existing dataset, a dataset where they already possess the verified final answer. They provide the model with a few brief textual examples of how a sequential query process should look just to format its output, and then they instruct the model to attempt to solve the new question by generating its own subqueries and retrieving documents.
But since the model hasn't been fine-tuned on this exact process, yet its initial attempts are going to be highly inconsistent.
Highly inconsistent. It will make logical errors. It will generate poorly formatted queries. It will retrieve irrelevant documents. So the methodology does not rely on a single attempt. The researchers configure the system to generate multiple different parallel attempts simultaneously for the exact same question. They might have the model generate 16 distinct sequences of subqueries and subanswers.
Okay, so 16 distinct textual paths attempting to reach a conclusion.
Yes. In some of those sequences, the model might query the director instead of the actor. In others, it might fail to extract the college name from the retrieved text. But probabilistically, in a small fraction of those 16 attempts, the model will happen to generate the correct sequence of subqueries, retrieve the correct documents, and output a final string of text that perfectly matches the known verified answer from their dataset.
So it's essentially running multiple parallel generations to see which sequence of text happens to result in the known target string. But how does that become high-quality training data? If it's just generating random sequences, isn't that data inherently noisy?
That's where the rejection aspect of the methodology is applied. Because the researchers possess the verified final answer, they use it as an automated filter. They programmatically evaluate the final output of all 16 generated sequences. If a sequence ends with an incorrect text string, that entire sequence of subqueries and subanswers is completely rejected and deleted.
Okay, so they discard the failed paths. But even if a sequence arrives at the correct final text, couldn't the model have just generated a lucky guess based on flawed logic? How do they filter out technically correct but logically flawed sequences?
That is a critical methodological detail in the paper. They don't just filter by the final text match. They implement a statistical verification step using log likelihood.
Log likelihood. Let's explain that term verbally without the formulas. What is that metric actually measuring in this context?
In language modeling, every time the system generates a token or a word, it calculates a mathematical probability distribution across its entire vocabulary. It assigns a numerical confidence score to the word it is selecting based on the preceding text. Log likelihood is essentially a measurement of that internal confidence.
So if the model generates a sequence of text where the internal probability scores for those specific words are very low, it means the model is statistically uncertain about its own output.
Exactly. Even if that low confidence sequence coincidentally ends with the correct final answer, the methodology flags it. The researchers calculate the average log likelihood for the text generated within the intermediate steps. They only retain the sequence if the final answer is correct and the mathematical confidence score of the intermediate reasoning text exceeds a specific threshold.
That makes perfect sense. They are filtering for sequences where the statistical probability strongly supports the logical progression of the text, not just random generations that happen to hit the target string.
Yes, it ensures that the generated training data represents a highly probable, logically sound sequence of retrieval and extraction. And by automating this process across thousands of questions, they successfully generate a massive new data set. This dataset no longer just contains question and answer. It contains question subquery 1 retrieve document, 1 subquery 2 retrieve document 2, and final answer.
Right, so they have successfully solved the chicken and egg problem. They computationally generated the intermediate steps. That leads directly into the second major methodological phase, which is the actual training process. They take this newly generated data set and use it to fine-tune an existing open source model. The paper specifically cites using Llama 3.1-AB instruct.
Yes, they use that specific model as their base. And the methodology details a unified, multitask learning approach. They are not just training the model to generate a single block of text. They format the training data to teach the model 3 distinct sequential behaviors simultaneously.
Okay, let's break down those 3 behaviors. What is the first specific task it learns?
The first task is next subquery prediction. The model learns to analyze the original question along with any previously retrieved text and formulate the exact string of text necessary to query the external database for the next missing variable.
So it's learning the syntax and structure of an effective search prompt. What is the second task?
The second task is sub-answer prediction. After the retrieval system returns a document, which might be a long block of text containing mostly irrelevant information, the model learns to analyze that document, isolate the specific string of text that answers its previous subquery, and output just that relevant string.
It's learning to extract the exact factual data from a noisy input rather than just processing the entire document globally.
Correct. And the third task is final answer prediction. The model learns to evaluate all the accumulated subanswers and determine if it has sufficient information to address the user's original complex prompt. If it does, it synthesizes the extracted text into a final coherent response.
That evaluation step seems incredibly important. The model has to know when to stop generating subqueries, otherwise it could theoretically just continue querying the database, indefinitely generating endless tangential searches. How does the methodology explicitly teach the model to stop?
The paper describes a specific learning to stop mechanism. It relies directly on the structure of the training data they generated, because the high-quality sequences they retain always terminate immediately after the final necessary piece of information is retrieved. The model learns that specific textual pattern.
It learns the statistical correlation between having all the required variables and generating the final answer token.
Yes. Mathematically, as the model's context window fills with the necessary sub-answers, the probability distribution shifts. The probability of generating another specific subquery token drops significantly, and the probability of generating the tokens associated with the final answer formulation increases until it crosses the threshold and terminates the loop.
So at this point in the methodology, they have generated the data and they have fine-tuned the model. There's a functioning CoRAG system. And this brings us to the third phase detailed in the paper, which focuses on inference, or what they term test time scaling. This concept of test time computation is extremely prominent in current AI research.
It is the primary focus of a lot of advanced systems right now. The fundamental concept is that you can predictably increase the factual accuracy of a model's output by deliberately allocating more computational resources, more time, and more processing power to the generation phase.
The idea that instead of generating the first highly probable token, immediately you force the model to compute multiple distinct textual sequences before committing to an output.
Exactly. CoRAG introduces specific decoding strategies that allow operators to modulate how much computational power they want to expend on a single user query. The methodology outlines 3 distinct strategies for generating the final text.
Let's examine each of those strategies carefully, starting with the most basic one. They describe greedy decoding.
Greedy decoding is the standard, highly efficient method. In this strategy, at every single step of the sequence, whether it's generating a subquery or extracting a subanswer, the model simply selects the single most mathematically probable token and moves immediately forward. It generates one single linear sequence of text.
It just takes the highest probability path without exploring any alternative options.
Right. It is computationally inexpensive and very fast. And for many queries, that primary high probability path is factually correct. However, the methodological weakness of greedy decoding is that if the model generates a slightly inaccurate subquery early in the process, it is locked into that path. It cannot correct itself if the subsequent retrieved documents are irrelevant.
It commits to the sequence and follows it to a likely incorrect conclusion. So to mitigate that, they detail a second strategy called best-of-n sampling. How does this methodology change the generation process?
In best-of-n sampling, the system does not generate one single linear sequence. It is instructed to generate a specific number n of independent full sequences simultaneously. For example, it might run 8 distinct query and retrieval sequences in parallel.
But if they're all running the exact same model, won't they just generate 8 identical textual sequences?
The methodology prevents that by introducing a parameter called temperature. They increase the temperature setting above 0, which introduces a controlled level of statistical randomness into the token selection process. So sequence A might select the most probable subquery, but sequence B might select the second most probable subquery, resulting in a slightly different text string.
So sequence A might query the cast of the movie while sequence B queries the actors in the movie. They take diverging textual paths. But ultimately, you end up with 8 different final generated responses. How does the system automatically evaluate which of those 8 textual outputs is factually correct when it no longer has an answer key to check against?
That is a very specific methodological innovation in the paper. They cannot verify the text against a known truth during the inference phase. Instead, they evaluate the sequences based on the success of their internal retrieval steps. They apply a mathematical penalty score to any sequence that generated a query and received a string of text indicating no relevant information found.
Oh, so if a specific sequence generated multiple queries, but the database repeatedly returned empty or irrelevant documents, the system automatically downgrades the priority of that entire sequence.
Exactly. The methodology relies on a heuristic assumption. It assumes that a textual sequence which successfully formulated queries, retrieved documents containing relevant data, and extracted coherent subanswers is statistically much more likely to be factually accurate than a sequence that failed to extract data from the database. It selects the final output from the most successful retrieval path.
That is a very logical constraint.
Yeah.
And then the paper details the third and most complex inference strategy, which they call tree search. This seems to be the most computationally intensive approach.
Tree search is significantly more complex. Rather than running completely independent parallel sequences from start to finish, tree search uses a methodology called breadth-first search to evaluate options sequentially.
Let's explain the mechanics of a breadth-first textual expansion clearly. How does the system manage the text generation?
The system starts with the original prompt, but instead of generating one first subquery, it generates multiple potential first subqueries, let's say 3 different textual options. The system then executes all 3 of those queries against the database simultaneously.
Okay, so it retrieves 3 distinct sets of documents.
Then the system evaluates those 3 retrieved document sets. It analyzes the text to determine relevance. If one of those queries returned completely irrelevant data, the system immediately terminates that specific textual sequence. It prunes it. It only retains the sequences that returned viable intermediate data.
So it discards the dead ends immediately rather than processing them to the end.
Yes, and then from the remaining successful sequences, it generates the next set of multiple subqueries. It iteratively expands the possibilities, evaluating the textual returns at each step, and discarding the paths that fail to retrieve relevant data.
It's mapping out multiple sequential steps in advance and dynamically updating its path based on the quality of the retrieved text. But computing multiple queries at every single intermediate step must consume an enormous amount of processing power.
It requires a massive increase in token generation and computational time. However, the methodology demonstrates that this intensive process yields highly predictable improvements in factual accuracy. The paper describes a log-linear relationship, essentially a consistent Pareto frontier.
Which means there is a mathematically consistent correlation between the amount of computational power you allow the system to use and the factual accuracy of the final generated text.
Correct. The methodology proves that by increasing the complexity of the decoding strategy from greedy to best-of-n to tree search, you achieve higher accuracy scores on complex datasets purely by expending more computational resources.
I want to return to a specific methodological scenario we discussed earlier. What exactly happens in this framework when a database search fails? Because even with an expansive tree search strategy, sometimes a specific textual query just doesn't return a matching document. The paper emphasizes a capability they call query reformulation.
Yes, query reformulation is a defining characteristic of the CoRAG methodology. In standard RAG, if the retrieval system returns a string indicating no relevant text, the generation process usually falters. The model either outputs a statement of inability or it generates hallucinated text based on internal parameters.
It interprets the empty retrieval as a catastrophic failure.
But the CoRAG methodology trains the model to process that specific failure string. No relevant information found as a dynamic textual input.
Meaning the failure itself becomes part of the context window.
Exactly. The model reads that failure string evaluates its previous subquery and autonomously generates a reformulated text string. There is a specific methodological example detailed in the paper regarding the actor Edward G. Robinson.
All right, let's look at how the model processes that specific textual sequence.
In one of the generated sequences, the model outputs the subquery, "Where did Edward G. Robinson go to college?" The retrieval database processes that string and returns no relevant documents. Perhaps the specific text in the database uses the word attended instead of the phrase "go to college."
So a standard model would stop generating useful text at that point.
But the CoRAG model processes the failure string and immediately outputs a newly formulated subquery. It generates the text, "What college did Edward G. Robinson attend?" or "Edward G. Robinson higher education."
It alters the vocabulary and syntax of the prompt to attempt a different mathematical vector match in the database.
And that reformulated textual query successfully matches a document retrieving the necessary data. The model learned this specific behavior during the rejection sampling phase we discussed earlier.
Because during that data generation phase, the random sequences that encountered a failed search and simply stopped generating queries were ultimately rejected by the final answer filter.
Exactly. The only sequences that survived the log likelihood and final answer filters were the ones where the model successfully reformulated its vocabulary after a failure and eventually retrieved the target text. So the fine-tuning process explicitly reinforces the behavior of persistent query modification.
It methodologically links search failure to textual reformulation rather than generation failure. Now, processing all these individual sequential queries seems technically demanding. A logical question arises regarding alternative methodologies, particularly the use of massive context windows. We currently have models capable of processing over 1 million tokens of text simultaneously. Why does the methodology rely on iterative subqueries instead of simply inputting an enormous volume of database documents directly into the initial prompt?
The paper explicitly compares the CoRAG methodology to long context approaches. The fundamental issue is the difficulty of extracting highly specific factual data from an overwhelming volume of text. Even models with massive token capacity struggle with precision when required to isolate one specific sentence buried within hundreds of pages of irrelevant documents.
The surrounding irrelevant text essentially degrades the model's ability to focus on the necessary variables.
Yes, the excess data dilutes the statistical probability of the correct tokens. The CoRAG methodology relies on precision. By iteratively querying and extracting only the specific sentences required for the immediate logical step, it maintains a very concise, highly relevant context window.
It filters the data at the database level rather than forcing the generative model to process all the noise.
Additionally, there is a significant computational cost consideration. Processing 1 million tokens of text for every single user query requires an immense amount of continuous processing power. Executing 3 highly targeted subqueries and processing only a few paragraphs of relevant text per step is computationally much more efficient.
That makes methodological sense. The paper also discusses comparisons to OpenAI's O1 model, which is currently recognized for its advanced reasoning capabilities. How does the CoRAG methodology contrast with that system?
The authors position CoRAG as demonstrating an O1-like reasoning process, specifically regarding the concept of test time scaling and sequential processing. Both models utilize intermediate generation steps before outputting a final answer.
But the internal mechanics of the generation process are different.
Very different. The O1 model operates largely as a closed system. It generates internal reasoning tokens to process logic, but it does not inherently rely on external textual retrieval during that process. The CoRAG methodology is explicitly designed around external database queries.
So CoRAG is methodologically anchored to verifiable retrieved text, whereas the closed model might rely more heavily on the internal statistical weights of its parameter training.
Correct. CoRAG documents its logical progression by outputting the exact queries and the exact retrieved text at every step and providing a transparent and verifiable chain of factual data.
I think it's important to also critically examine the foundational assumptions of this methodology. Every technical paper relies on certain premises being true. What are the primary assumptions the authors make for this framework to function?
There are two critical methodological assumptions. The first assumption relates directly to the data generation phase. The entire rejection sampling process fundamentally assumes that you have access to a large data set of complex questions that already includes the verified correct final textual answers.
Because the automated filtering mechanism strictly requires that target string to evaluate the generated sequences.
Yes. If you are attempting to train a model in a specialized domain where those verified final answers do not already exist, you cannot automatically filter the sequences. You wouldn't know which textual paths were factually correct. The methodology requires a pre-existing verified dataset to bootstrap the intermediate query training.
That is a significant constraint. You must have the final data to train the sequential process. What is the second assumption?
The second assumption underpins the test time scaling strategies. The methodology assumes a direct positive correlation between increased token generation, meaning longer sequences of subqueries and extended tree search evaluations, and improved factual accuracy.
It assumes that generating more intermediate text inherently leads to better logical synthesis. Does the data fully support that assumption?
Within the parameters of their testing, the experimental data strongly validates the assumption. The performance metrics demonstrate a clear upward trajectory as computational limits increase. However, mathematically, there must be a point of diminishing returns. An infinite loop of textual generation would eventually introduce errors or deviate from the original prompt. But within the practical limits tested, the methodological assumption holds true.
Let's discuss those specific performance metrics. After defining the generation process, the unified training, and the inference strategies, how does the finalized CoRAG methodology perform against standard models?
The researchers evaluated the system using the KILT benchmark. KILT is a comprehensive collection of highly complex data-intensive tasks, including multi-hop reasoning, fact verification, and specific entity linking. It is a standard, rigorous evaluation for retrieval models.
And what were the specific results of that evaluation?
The CoRAG system achieves state-of-the-art results across the majority of the benchmark datasets. It successfully outperformed models with significantly larger parameter counts. But the most prominent methodological validation occurred on a specific dataset called music.
Music is the dataset specifically engineered to test multi-hop reasoning, right?
Yes, it is structured to explicitly defeat models that attempt to answer complex questions in a single generation step. On that specific dataset, the CoRAG methodology improved accuracy scores by over 10 absolute points compared to highly optimized baseline systems.
A 10-point increase in an established benchmark is a massive statistical improvement.
It is a profound validation of the sequential query methodology. It statistically proves that for multivariable questions, iterative textual retrieval is significantly more effective than single-step processing. There was also another technical result in the data regarding model scale that is very important. They documented a phenomenon called weak-to-strong generalization.
Let's clearly define what they mean by weak-to-strong generalization in the context of their training methodology.
During the rejection sampling phase, they must use a base model to generate the intermediate textual sequences. The researchers tested whether they could use a smaller, less computationally demanding model, the weak model, to generate the training data sequences, and then use that data to fine-tune a much larger, more capable model, the strong model.
The logical risk there would be that the smaller model generates lower quality textual reasoning, which might degrade the performance of the larger model during training.
Exactly. And the data showed that if the base model is too small, for example, they tested a 1 billion parameter model, it fails to generate statistically viable reasoning sequences. The text is too flawed for the log likelihood filter to extract enough useful data. However, they found that utilizing a mid-range model, specifically a 3 billion parameter model, successfully generated high-quality textual sequences.
And that data was sufficient to successfully fine-tune the 8 billion parameter model.
Yes, the larger model learned the methodology effectively from the data generated by the mid-tier model. This is methodologically crucial because it proves the data generation process is scalable. You do not need to expend massive computational resources running the largest possible models just to generate the training sequences.
It makes the entire framework technically accessible and cost-effective to implement. So to synthesize the core technical points of this deep dive, the CoRAG methodology represents a fundamental shift from a single-step retrieval process to an autonomous iterative processing framework.
Yes, and we can explicitly summarize the 4 primary methodological phases. First, the system utilizes rejection sampling to autonomously generate intermediate training data filtering random textual sequences by log likelihood and target answer verification.
Second, it implements unified multitask learning to fine-tune a model to sequentially generate subqueries, extract specific text from retrieved documents, and evaluate when to output the final generation.
Third, it employs flexible test-time decoding strategies like greedy decoding and tree search, allowing operators to modulate computational expenditure to maximize factual accuracy.
And fourth, the methodology explicitly trains the model to utilize query reformulation processing failed database retrievals as dynamic inputs to generate altered search syntax.
That is the complete methodological structure of the CoRAG framework.
It clearly demonstrates how the architecture of AI systems is evolving to prioritize sequential, verifiable data processing over simple statistical word prediction.
It is a critical development in creating systems capable of executing complex multi-step data analysis autonomously.
And looking at that established correlation between computational expenditure and textual accuracy during the test time scaling phase, it introduces a fascinating implication for the future of these systems. If factual accuracy is directly dependent on the volume of processing power allocated to a specific query, we may be transitioning toward a technological infrastructure where the precision of the verifiable truth a system outputs is strictly determined by the amount of computation a user is willing or able to finance.
The methodology certainly suggests that higher degrees of factual verification require proportionally higher computational costs.
A compelling technical reality to consider as these systems scale. Thank you for thoroughly analyzing the methodology of this paper with us today.
It is an excellent framework to break down.
And thank you for listening to this deep dive. Keep questioning the fundamental processes behind these systems, and if the initial output lacks verification, perhaps formulate a more specific query. We will see you in the next deep dive.